Hello, I'm Doug Cotton, the author of this book, Why It's Not Carbon Dioxide After All. Quite a controversial book. You can read a bit about me on the background there, on the back cover. Have you ever wondered about this greenhouse effect and whether carbon dioxide is really causing the problem? Or is it all just natural? If we look at a website by Dr. Roy Spencer, a climatologist, he keeps some records of sea surface temperatures, lower troposphere as we call it, in the lower atmosphere. And you'll see that since 1998, where we had quite a maximum, this red line gives you a moving average. We're actually cooler than we were back in 1998. And it's not a tremendous increase anyway. There have been increases like this way back. Before, for example, the medieval warming period, nearly 1,000 years ago, we had prior to that a Dark Ages cooling period, roughly 500 years before that. So, of course, there was some warming between that Dark Ages period and the medieval warming period. And then, after that, temperatures went down again towards what they called the Little Ice Age, where they skated on the River Thames in London. And that was roughly 400 or 500 years back, and since then it's been increasing gradually, but we're only talking about a long-term increase of the order of just over a degree or degree and a half or so. We are probably approaching a long-term natural maximum sometime in the next 100 years. Some scientists think that it could be in the 2030s, around about the maximum, and then it will start to cool for perhaps 400 or 500 years. And these cycles, we believe, are probably in some way or another related to things such as the variation in the solar radiation, perhaps the variation in cosmic rays, which might affect cloud formation, and whatever the reason the clouds might vary, they can be also due to natural variations in the percentage of cloud cover, which therefore casts a shadow on the Earth, and the more there is, the cooler the Earth will be. And all of these natural factors could very easily account for 1 or 2 degrees of long-term cooling in a cyclic effect. There's also a superimposed cycle that's more like about 60 years in length, and in the 30 years or so towards the end of last century, both the long-term cycle and that short-term 60-year cycle were both on the increase, and so that made people somewhat alarmed that, perhaps this rate of increase would continue forever. Well, this is it back here before the turn of the century, but broadly speaking, it's levelled out now because the 60-year cycle is actually going down, the long-term one's perhaps still going up, and the net effect is perhaps a very slight decline in temperatures that will probably continue until roughly 30 years after this maximum back in 1998. Then we can expect maybe some more warming, but not too far into the distant future. There should be a reversal of all that long-term trend towards a long-term cooling effect. Now, why doesn't carbon dioxide have any effect? Well, basically the whole philosophy of the greenhouse radiative forcing concept, as they call it, is based on a concept that radiation from carbon dioxide somehow, along with radiation from water vapour, somehow helps the sun to raise the temperature of the Earth's surface. Now, it can't actually do that because the radiation is coming from a colder atmosphere, and to actually raise the temperature each morning of the surface, you would have to add energy, thermal energy, and that energy is represented by the movement of molecules. They move faster between collisions, and they vibrate faster and rotate faster, and we call it kinetic energy. Basically, radiation itself does not actually carry this kinetic energy because it doesn't actually involve any molecules. It travels through space. It carries what we call electromagnetic energy. So the radiation is originally created when photons move within electrons and drop down between different levels and emit what they call photons, a little burst of radiation. And effectively what's happened is that the kinetic energy or thermal energy within the source of the radiation has in fact been converted into the type of energy that radiation carries, which we can call electromagnetic energy. Now the point is when it strikes a warmer target, that electromagnetic energy is not actually converted into the kinetic energy at all. And if it were, it would violate what we call the second law of thermodynamics, because it would actually amount to an effective transfer of some thermal energy in the other colder source, which became electromagnetic energy, which then goes back to becoming thermal energy that's supposedly warming up a target that was actually warmer than the original source of the radiation. And that just simply can't happen in physics, but the infant scientists of climatology would like you to believe that it could. Now, some of them say, oh, well, all it does is slows down the rate of cooling of the surface. Now, there's an element of truth in that. The cooling of the surface is due partly to radiation, but also partly to other things, such as evaporative cooling of the oceans and just the simple transfer of energy by molecular collisions at the interface between the surface and the atmosphere. And these other processes, which we call non-radiative processes, basically also help to cool the surface, and they in fact transfer about twice as much energy from the surface into the atmosphere as does the radiation. Now, all that can actually happen is that the back radiation, as they call it, the radiation from the colder atmosphere, can slow that portion of the cooling of the surface which is due to radiation, assuming that surface is warmer than the source of the actual radiation in the atmosphere, and it normally is because the atmosphere gets colder as you go up, as you know. In that sort of situation, yes, it can cool the radiative cooling, slow the radiative cooling, but it can't slow the other cooling, and the other cooling can actually speed up, and so the net effect may be nothing at all. Or even if it isn't quite the case, it will still not necessarily make the minimum temperature at night any colder or any warmer, because the cooling might just take a few minutes longer into the evening, but it will still come down to what we call a base or supporting temperature. You can see this very clearly in an island like Singapore, where the minimum temperature for each night of the year is very rarely below 25 degrees. That's a supporting temperature. And for that matter, it very rarely goes above 32 degrees for the maximum almost any day of the year. So you just have this narrow variation, and that's all that the sun can achieve. Even right up there in the tropics, just 2 or 3 degrees, I think, from the equator, the sun cannot raise the Earth on Singapore above about 32 degrees centigrade. So how powerful is the sun? And is the sun really doing it? Well, there are two questions to answer here. And the strange thing is, when we actually work out how much radiation from the sun gets absorbed into the surface or strikes the surface, may not necessarily all get absorbed, we find that it really would not be enough on average to raise the temperature to anywhere near what the temperature really is. I won't go into the detail, but in physics there's a thing called the Stefan-Boltzmann relationship or law, and you can look it up on the website if you like, and search for Stefan-Boltzmann calculator, look up the one under Tutor Vista, and you can actually put in a flux of 168 watts per metre squared, as it's been worked out to be, and you'll get a temperature of minus 40 degrees centigrade. Now people might say, but the sun's much brighter in other areas, and we know it can make the surface, 40 odd degrees in some regions, but that's only a very small region of the Earth at any one time. And the effect on the overall mean, in fact, would be to lower the mean, not raise it, because the fact that the radiation varies so much means that the effective mean temperature that it achieves is actually lower than if it was shining on a flat Earth with a constant amount of radiation. And that's to do with the fact that the actual flux of radiation has to go up with the fourth power of the temperature, or putting it round the other way, the temperature that a certain amount of radiation achieves is proportional to the fourth root of that radiation. So if you use up a lot of your radiation that contributes to the mean in the higher temperature ranges, then effectively the end result is that the mean is less. And you can prove that by selecting a few values and putting them into that Stefan-Boltzmann calculator if you're interested in doing that. So effectively the International Panel of Climate Change is assuming that the Earth is flat and receives constant radiation. But furthermore, they are assuming that we are adding to that solar radiation about twice as much radiation from the cold atmosphere. And the total effect of the two lots of radiation is supposedly what is explaining a mean temperature of 15 degrees throughout the whole globe. Well, as I said, it wouldn't be 15 degrees, even if you could add the back radiation. It would be probably only about 3 or 4 degrees because of the fact that the radiation varies dramatically, and so would the radiation from the atmosphere. In fact, it's so ironic because if you do add the back radiation when you're doing all your calculations to get the mean of the 15 degrees, then if you look at a place in the tropics that actually could be receiving, 800 watts directly from the sun on a clear sunny day with no clouds and the sun's directly overhead, and it could be receiving in back radiation maybe 400 or 500 or more watts, you get a ridiculous answer. You get temperatures up around 90 to 100 degrees Celsius, and of course we know those just don't happen. So that in itself is proof enough that you don't add the back radiation. So really they are very stumped. What they say is that the radiation from the atmosphere somehow raises the surface temperature from about minus 18 degrees to this plus 15 degrees, in other words by about 33 degrees. And they say this is all due to greenhouse gases. Well, what's the most prolific greenhouse gas in the atmosphere? It's water vapour. Water vapour varies between about 1 and 4% in the atmosphere. The average is probably only around maybe 1.5% or so, but basically they're saying that water vapour is doing most of that warming of the surface because the amount of carbon dioxide is only 1 molecule in every 2,500 molecules at 0.04% compared with something like 1 to 4%. So there's far more water vapour, and so it must be doing most of that 33 degrees of warming. Let's suppose that there's 1.5% in the atmosphere on average, and let's suppose the water vapour is doing 30 degrees, then what they are saying is for every 1% we're getting a 20-degree rise in temperature due to water vapour. Okay, well let's look at a rainforest that has 4% water vapour and compare that with a dry region with only 1% at a similar latitude and altitude and the same time of the year. And if 1% is causing 20 degrees of warming, then the difference of 3% between these two places should represent a difference in temperature of 60 degrees, which of course is absurd. The rainforests aren't warmer, they're in fact cooler. And that's the absurd situation. Now we can look at my website here, which is climate-change-theory.com, and we can look at a paper that I wrote called Planetary Core and Surface Temperatures. And that paper, written back in early 2013, has at the back of it a little study. Here's the contents here. And if we go right down to the study at the end, we will see that in fact regions that are wetter have lower average minimum temperatures. Here are the wet regions with a minimum of 20.1 and a maximum of 30.8, and you see lower maximum temperatures also for the wetter regions. So in fact, increasing the amount of water vapour coming down here towards the wet regions lowers the temperature. Water vapour cools, it does not warm as the IPC claim it does, and it certainly doesn't warm and make a 60-degree difference between these dry regions and these wet regions, putting the wet regions way up here and the dry ones down here. It's absolutely absurd. And that is the kind of pseudoscience that you're up against when you're talking about this so-called greenhouse effect. Well, what does happen? And the answer to that is in a totally different paradigm altogether. It's basically got very little to do with radiation. And we know that when we think about other planets. If we look at the planet Uranus, it has a troposphere like us. It's a nominal troposphere. It doesn't actually have a surface at the base, and it's a troposphere that is 350 kilometres high, whereas ours only varies from about 8 to 17 kilometres above the equator there. Now, Uranus is also about 30 times as far from the Sun, and that means it receives only about 1 over 30 times 30, 1 over 900 of the actual radiation, just over 1,000th of the amount of radiation that Earth receives. But at the base of that nominal troposphere, the temperature is hotter than Earth, around about 50 degrees or so. Why is it so? Oh, is Uranus just cooling off? No. There's no significant evidence of any, convincing evidence of any significant loss of energy. And it's not contracting like the planets like Jupiter that are converting gravitational potential energy into kinetic energy, in other words heat, and emitting more than they receive. No, that's not happening with Uranus. A totally different process is occurring, and it occurs on all planets. It's just not quite so obvious on Earth because we stand in the sun and we think we're getting warmed by the sun, and sure we do in some locations a little bit, but broadly speaking, the sun is not what raises the temperature. If you were on the surface of Venus, you would be receiving only about 10% as much solar radiation as you do at the surface of Earth. And yet the surface of Venus is well over 460 degrees, and it's a totally different kettle of fish, but these are the cases on Uranus and Venus because the atmosphere is much higher. Now, what actually happens, as it's explained in this book, is that the force of gravity acts upon molecules when they're in motion between collisions. And what that does is create a temperature gradient in a planet's troposphere. And that gradient, where the temperature cools by around about 7 degrees or so each kilometre, is actually a state of equilibrium, thermodynamic equilibrium, or to the physicists it's a state of maximum entropy, which is what the second law of thermodynamics tells us will tend to happen. And that happens when the sum of potential energy and kinetic energy is constant. And if you look at this graph on page 22, I'm turning it this way so that line along the bottom, that green strip representing potential energy plus kinetic energy of molecules, is roughly horizontal. And when we add new energy like that little red triangle, and that could be solar energy absorbed in the upper atmosphere where the sun can actually raise the temperature of the molecules that absorb that radiation in the upper troposphere because they're cold enough to be raised in temperature, then that new energy will spread out, and it spreads out rather like in the diagram on the right here, and some of that energy will in fact move up this sloping thermal plane because there it is when we look at the temperature axis being vertical, it's getting warmer as you go to the right, and so some of that new energy can actually go from cooler to warmer regions. And you might think that this obeys the second law of thermodynamics. You learnt in school, oh, heat only goes from hot to cold. But really what you learnt in school is just a corollary of that second law. It's something that only applies in a horizontal plane. The second law is really all about entropy, and this strange thing called entropy increases towards a maximum. And basically entropy can be thought of as a measure of the progress towards that maximum state of entropy. It can also be thought of as the dissipation of differences in energy. Different energy potentials will automatically tend to dissipate until they reach zero, and at that point we have maximum entropy. So entropy is a measure of the dissipation of the differences in these energy levels, and entropy is affected by both gravitational potential energy and kinetic energy. And so what it boils down to is that when we have this state of maximum entropy, which the physicists call thermodynamic equilibrium, we in fact have a homogeneous, a uniform sum of potential energy and kinetic energy, as I showed you in the diagram in the book. And that means that at one altitude, if your potential energy plus kinetic energy adds up to a certain value, then it will add to the same value at a lower altitude. But at the lower altitude, the potential energy is lower because it's closer to the surface. We're talking about gravitational potential energy of the molecules. And therefore the kinetic energy is higher, but it's only the kinetic energy which contributes to the temperature. And that's what it's all about. Because the potential energy varies, and yet the sum of the potential energy and the kinetic energy is constant, the kinetic energy itself must vary in such a way that we have warmer temperatures below and cooler temperatures at the top. Now there's a little bit of modification when you introduce these so-called greenhouse gases, which actually can radiate, whereas oxygen and nitrogen don't tend to radiate very much at the normal sort of temperatures we find in the troposphere. Basically, that radiation, mostly between other molecules of the same type, will have a temperature levelling effect which will work against this gravitationally induced temperature gradient. So the gravitationally induced temperature gradient, where PE equals KE, can be shown to be about 9.8 degrees per kilometre. But in fact, in reality, we have averages around about 6.5 or 7 or so degrees per kilometre because of the temperature levelling effect, primarily due to water vapour, but just partly due to carbon dioxide. And that therefore reduces the slope of the temperature gradient a little bit. But the whole temperature plot or graph in the troposphere will rotate about a sort of central point so that the radiation, the total radiation with the sun, keeps in balance with the amount of radiation that's coming in. And so that means that the temperature will be lower at the surface end. And of course it's well known that water vapour reduces the magnitude of this temperature gradient, and the climatologists know that. So how they imagine that it could reduce that temperature gradient and yet at the same time increase the whole level of the thermal plot at the surface end, that's going to jack up the whole plot from something like this to something like this, and the area under that plot is going to be much bigger, and that represents far more radiation going back to space, and not only would that have a cooling effect, but it would no longer be in balance with the incoming solar radiation. So the whole thing is wrong. And what is correct is the fact that gravity forms this temperature gradient in any planet's troposphere, and that enables new energy